as important as it is for us to have the probability distribution for a random variable, such as the time between vehicles in that pedestrian crossing example, it's a little bit burdensome to have to carry around this whole big mathematical expression. And it's, even though it's valuable to have the graphical representation of this same equation, it still isn't very particularly useful in communicating in a very quick, simple manner some other important descriptors of the random variable. This is certainly the genesis of all these other descriptors that we might have, but is there any way that we can summarize this in a quick, simple, direct way? Or what are some of the important properties of these, or descriptors of this random variable? And those really come down to trying to address two different kinds of questions. And one is a measure of center, and the other is some sort of measure of spread or dispersion. And we'll put both of these in quotes because we're not trying to be too precise here. This is more of a qualitative kind of sense. Now, of course, the first thing that might leap to mind is, well, can't we just find the average value? And certainly that's where we're headed, is this notion of what we call the mean. But it's a special kind of average. There are a lot of different averages that are running around out there. And when we're talking about a population, then in a sense the population being the theoretical values of our random variable, not what we've observed, but what's out there in the total population. Then we use this Greek symbol lowercase mu almost exclusively. Almost everybody uses that particular one if they're using a Greek symbol. Sometimes they'll use a lowercase m instead, and that's just maybe more historical. When typesetting days, the Greek font wasn't so easily available to the typesetter. These days, you almost always, I can't think of an occasion in my own practice where I have not seen for the population somebody use the symbol mu. I'm sure it's out there, but I have not personally encountered it. Right? And this mu, this way to find this average, which is really ultimately a centroid, or center of mass, and that last phrase will be quite helpful in understanding why the mathematical function here turns out to be what it is. That mu is going to be equal to our possible values of a random variable, and we'll stick with what we're doing up here, that t is our interarrival time of our vehicles. Right, that we're going to take all the possible values of t, and since now discrete outcomes, so t sub I, and we're going to weight them by how likely those are to occur. Right, so that's the special averaging in this sense, that we're going to weight all the individual outcomes by how likely they are to occur and sum all those up. And that is our average, or our mean, or what you'll also learn here in a moment, we sometimes call the expected value. And being a center of mass, notice that we're going to weight each possible outcome by the probability mass, hence this notion of center of mass. And you could do this fairly simple. The answer for the centroid of this particular one is pretty obvious, given that it's symmetric about 9. With equal probability mass on either side and spread out in an equal kind of way. But in terms of how to calculate that out by long form, one possible outcome is 3 times its chance of occurring, which is 1/9, plus 6 times its chance of occurring of 2/9, and 9 times 3/9 plus 12 times 2/9 plus 15 times 1/9, and that will, when you work it all out, be exactly equal to 9 seconds, as we would have anticipated from this concept of centroid of mass and notion of center just by looking at the graphical form here. A measure of spread is the variance. And for reasons that will become more apparent here in a second, that's going to be given a symbol that has a square in it, sigma squared. Right? And that's going to be our measure of dispersion or spread, or at least one form of it. And sigma square now is going to be, or what we're really trying to figure out is, well, how much is the random variable spread out from the mean? Right? And we don't want to bias on one side of the mean, high values or low values, or in other words, positive or negative values of that. So what we're going to do is we're going to take a random variable, we're going to subtract off the mean, and to get rid of that positive or negative values, high or low, so to speak, we're going to square those. So that becomes a squared deviation away from the mean, and then we'll weight those again by the chance that a random variable takes on one of those values and sum that up over all of our possible outcomes. Right? And so here for our pedestrian crossing problem, then we would get 3 minus 9 squared times 1/9 for a chance that we have the 1/9. Mu is 9, right? I'm sorry, chance that we have a 3-second gap is 1/9, and the mu is 9. And then we do that for all these other ones as well, changing the probability masses as we go. Note that in this case, our average, our centroid, was exactly equal to one of the possible outcomes. So 9 minus 9 will be 0, of course. That doesn't always have to happen, right? For a discrete random variable, in fact, in general, your mean will probably not be one of the possible outcomes. It's a notion of the center of mass, not necessarily the most likely value to occur. That's the mode. It's a different kind of thing, right? And then we have one more, or two more, that is, we've got 12 minus 9, that's squared, times 2/9, plus then 15 minus 9, that's squared, times 1/9. And when you work that out, you'll get that that's equal to 12 seconds squared, right? So notice the units, because we took the deviation away from the mean and then we squared it, we get square units there. And that's a little bit hard to work with and understand what it means. So we do the natural thing, and that is, well, okay, if we got squared units, why don't we take the square root of that? So sigma equal to the square root of the variance. And so that's a square root of 12. And that will be then 3.46 seconds or so. Right? And that is called the standard deviation. Right, given the symbol sigma. And that was why in the variance we had squared that. I'd actually looked ahead knowing that we were going to take the square root of that. And that's why that particular symbol is done that particular way. Okay, now that's all well, fine, and good, but what does a sigma, a spread of 3.46 mean? And one of the ways to understand that is to normalize it. And the way we do that is with something called the coefficient of variation. Now you're gonna there's no one common symbol for the coefficient of variation, although it is common that nobody likes to write it all the way out. So one way to make that shorter is with C period, O period, V period, all lowercase. Unfortunately, we have this thing called covariance when we have more than one random variable. And in that case, the covariance is oftentimes then a capital COV or capital C, lowercase ov. It's a crummy kind of deal because you've got two things that have similar letters and now they're case sensitive, right? Sometimes you'll see the symbol used of lowercase delta, kind of continuing on with the Greek symbol theme, but not always. And it's less common than, say, sigma and mu are almost always used for the population mean and population standard deviation. Right? And so the COV here in lower cases is equal to the spread or our standard deviation divided by the mean. And for us, that's going to be 3.46 divided by 9, and that's equal to about 0.38, which in my world is a fairly large coefficient of variation. If I'm looking at the coefficient of variation for the modulus elasticity of steel, that's going to be down around 10% or less, right? And this is reasonably high. On the other hand, if I'm looking at the coefficient of variation associated with, say, the peak ground acceleration in a strong motion earthquake, this COV is now going to be up around 100%, a lot larger than this. So to me, this is a fairly large number, although you could argue that maybe it's somewhere in the middle or so. Right? A lot of processes out there that aren't natural but are rather man-made kinds of processes, say manufacturing, this would be a fairly large kind of coefficient of variation. It's very helpful in the following kind of sense. For instance, let's take a look at a couple of different random variables that have their own mean and their own standard deviation. So random variable 1, let's say, has a mean of 100 and a standard deviation of 20. How big is that? Well, all right, the COV is going to be equal to 20%. And we look at a second random variable that has a mean of 1,000 but has the same standard deviation. And so relative to the mean, its spread is a lot less. And so if I'm including these two random variables, that now I have a third random variable that's somehow a function of these first two, and I'm trying to figure out how to go collect information and try to understand my third random variable, say it's a highly nonlinear function between those two to get to the third one, then I might be tempted, depending on what I think the relationship of the sensitivity is of the third one to these other two, I might be tempted to just ignore any variability associated with number 2, because the first one has so much more relative variability. Now, I try to qualify that because that's not going to be true in all instances. It depends upon the mathematical relationship between all of the different random variables. For instance, if I'm taking the second one and somehow raising it to the 4th or 5th power, but I'm only linear to the first one, well, then I'm very much more sensitive to this one. Right? Or if I'm taking the square root of the first one, right? Somehow minimizing what the spread is and influence on something else. But then, okay, those are some exceptions. But in general, if I'm looking at different random variables and I see orders of magnitude different in the coefficients of variation, I'll be very tempted to take the one that is smaller and treat that as a deterministic or a single value, maybe right at the average, or maybe I'll hedge it slightly, some other value. But I may, just for simplicity's sake, kind of ignore some of its spread, because relatively speaking, 2% COV is exceptionally small. I would love to have random variables that were down around, had a coefficient of variation around 2%.